Our next speaker joined Caterpillar Incorporated in 1988 and spent the last 20 years or so in the area of virtual product development. Kevin he serves as Caterpillar's liaison to NCSA and also is a member of the Council on Competitiveness, the HPC Initiative Manufacturing Working Group. Please join me in welcoming Kevin Hofstetter.
Good morning. It's an honor to be here this morning. This is actually the first year that I've been at this conference, so looking forward to a couple of very interesting days. So again, from Caterpillar, and along with what Mike had mentioned, I also manage our research budget for the virtual product development area. So what I'm going to do, cover several different topics, start off just a little bit of overview of the company, and then followed by some comments about our virtual product development, some of the goals, look at a future vision, and some of the hurdles that we have in the application of high-performance computing. I'm going to be focusing most on modeling and simulation. When we talk about high-performance computing, at Caterpillar and probably at many other manufacturers, even large manufacturers, we're usually 5+ years behind, maybe even 10 years behind what the leading edge is. So, Caterpillar, we are a global company, Fortune 500. In 2009, we had about $32 billion of sales. 2010, we were up to $42.5 billion. Over 225,000 employees. That includes both Caterpillar and also our dealer network, which is very strong. We have locations in over 50 countries. And products work in 180 countries around the world, so we are very global. We also have research facilities in multiple countries as well, in addition to the United States. If we look at Caterpillar itself, minus the dealer network, we've got about 93,000 employees, and half of those are based outside of the U.S. Along with that, again, I mentioned the research facilities. We have engineers somewhere in the order about 5,000 to 8,000 engineers, and there's some percent of those who are actively involved in modeling and simulation. It's a smaller percent. The product line, we have a wide product line. This just shows a few of the different products, just to kind of give you an idea of the size. So in the middle, we have one of our off-highway trucks. Those are very, very large trucks. The largest one will haul about 400 tons of material, has tires that are about 12 to 14 foot in diameter, and they sell for multiple millions of dollars. And you look at the bottom, we have some of our smaller machines. That's a skid steer there in the middle. That machine is very, very high volume, but then they're also price-wise, they're looking at tens of thousands of dollars. And so you consider the design hurdles between the very, very large to the very, very small, and considering the margins on the large machines very high, margins on the small machines very low. So there's a lot of variation in how we're able to design those various machines. We also are into engines, so we have diesel engines. Also, we have natural gas engines and industrial turbines. We have solar turbines out in California. Additionally, we are in other areas where we do have the financing leg and also logistics. We also are into remanufacturing and have recently purchased various businesses where we can expand that remanufacturing. Just a comment here from our Chief Technology Officer. We are focused on technology and understanding how we can use that technology to deliver value to our customers. And just to back that up, this is our R&D budget. As you look throughout the years, if you look at 2008, that was when the downturn hit. That was actually our highest R&D budget in the history of the company. After the downturn, 2009, we had the second largest R&D budget in the history of the company. So the company is strong on R&D, and even in the midst of one of our worst years since the Depression, we had the second highest R&D budget of the history. So our future does depend on successful product development, and we've got are dollars that show that we are definitely focused on that. If we look at virtual product development, so what I want to do is just spend a little time on the product development timeline. This is specific to Caterpillar, but it also, I think, can apply to many other large manufacturers. I apologize for this. The center one here doesn't look like the text is showing up well. But we start off with concept, we go to design, and then this one is build. We test, validate the machine, and then ultimately go to production. If we look back maybe 20, 30 years ago, we had this cycle was on the order of maybe 10 years for a new product. And we would go through maybe 3 iterations of this design, build, and test. We prided ourselves in the ability to be able to test our machines to the extent that we knew when we delivered them to the customer, went to production, that they would be right. That was extremely costly, and of course, the time frame, 10 years, we were able to compete very well in those days. Today, that has changed dramatically, and so we have to shorten that timeline in order to align with the competition. We also currently are in a product development mode where we're having to meet emission regulations, which sets a specific time when, if we do not meet those regulations, we don't sell product. Our product line, if you look back 20 years ago versus today we have about an order of magnitude more products, and in order to meet these emissions, we are having to redesign nearly every product in our whole product line. So that we don't have the liberty of doing this 10-year product design cycle anymore. So if we think about this design cycle, and we look at over time, if we're in the concept phase, and we think about the cost to fix problems. So we come up with a new product design. Our goal is to deliver it to production such that it's meeting all the expectations. We have all the problems worked out of that. If we look at the cost to fix these problems, depending on where we identify them and also the time to fix, if we're in the concept phase, it's very easy to make a change. As we start to get closer to building the iron and then ultimately test the validation and we go to production, the cost to change and to correct problems becomes extremely high, and the time to do that is very high as well. Along with this cycle, I might mention, we look at the production, and this chart would perhaps indicate that production occurs when we have all the bugs figured out and everything is correct, and then finally we decide to go to production. That's not the way things work. So production dates typically are set by marketing to say we are going to release on such and such day or such and such month. So what will happen, and this I think is the more significant curve, is the ability to optimize. We'll start off with a design and maybe we want to try a lot of new things in this design. If we're back in the concept phase and we're able to look at multiple concepts, we can optimize quite well, but we need to be able to evaluate those various concepts. As we get into iron, the ability to optimize starts to drop dramatically, and at some point, fixing the problem becomes putting Band-Aids on or dropping back to a prior technology when we wanted to put a newer technology on. So the ability to optimize, this is very significant. As we get closer and closer to iron and then to production, we lose our opportunity to optimize our product. So what do we do about that? We need to really drive the discovery early on in the design cycle, and this, of course, brings in modeling and simulation. We've been at the business of doing modeling and simulation for many years. I started over 20 years ago, and we were doing a lot of structural analysis at that time. Then we got into doing more system analysis and so on. But clearly, this whole modeling and simulation up front to gain knowledge is extremely important, not just at Caterpillar, but I believe at many manufacturers in the U.S. and across the globe. So if we look at some of the areas where we use modeling and simulation, there's many different areas. So all the way from our engines to our cooling systems, we have the linkages and the structures, drive trains. Then we get down to some of the smaller components, looking at fuel systems, controls, electronics, and there's quite a bit more that I could put on here. We do materials simulation and so on. And then finally we have to bring all those components together into a full system and understand the system design and system integration, and will this machine perform the way that it was intended to in the field. If we go to look at kind of a future vision, this is looking at our product development. I talked about our product development timeline, where we were in this mode of we design a product, we go out, we build a prototype, we go out and test it, and we keep in that loop until we finally say either we're ready for production or marketing says you will go to production. And then we got an issue. So we put the machine out, and this, I'm talking from a perspective of Caterpillar, but also this is very generic, I think, to many manufacturers, kind of in the same mode, is that we get the warranty back. Where we are moving now is to say, well, we designed this product, but let's do a virtual validation. And so now we're in this loop here where it was design, build, test with actual iron. We get in this loop with simulation. And so we design the machine, we do the virtual validation, we go around this loop, eventually we build, we test it, and we go to production, and there's dollars, but these dollars get smaller. Where we want to go is looking at this design by analysis. So where analysis drives the design rather than let's design it and then instead of going to test in iron, let's just do the test in simulation. The goal then, design by analysis, and then the goal is to build the prototype and test it, but that testing is only to confirm that what we did in our design by analysis was right. And potentially we would probably have a feedback here to say, well, if we can improve our simulations based on that test data, but we wouldn't expect to build the prototype and find that there are huge issues with our design. So this is kind of where we're on this path, and I think again there's many manufacturers that are on this same type of a path. And then way at the top, I'm not sure what this looks like, but if we think about where we want to go, is that we get to a point where we've modeled everything, and we look at simulation versus test. Simulation is more complete than test. Right now, if we take a machine, we take it to the field, we do our testing, and we have a number of sensors on that machine, but we can never put enough sensors on to understand the full machine. In simulation, we can do that. If our simulation is accurate enough, now we can extract far more data from the simulation than we ever would in a real test. And our goal then, modeling and simulation, it should be able to drive decisions at all different levels. This other one, a model with each of the components, this kind of connects in with potentially with the supply chain as well, is we have many different components. We come back within Caterpillar, we'd like to have a model of those that we could put in our system model. We wind up building those models ourselves. They may not be the most accurate. Ideally, we would have a situation where we get a component, we get a simulation model, comes right along with it. We can plug it back into our system simulation and assure that our product is meeting the requirements. So again, strong collaboration. And then modeling and simulation, high performance computing needs to come in at all levels. So we think about this product development, but what about when we get into our the costing or the marketing and all other areas of the corporation? We ought to be able to tie this all together. That is way beyond the scope of what I'm working on, but ultimately that, I believe, is where we need to go. So, looking at a few hurdles. If I look at from our perspective in the design space, scalability, we do have internal codes we're developing. Scalability is an issue, but the scalability in many of these problems, we have the resolution that's appropriate, but we're running an order of magnitude slower than what we need to. So we need some very strong scaling in several of these different codes. And then if we look at the ISV codes, licensing is a tremendous issue. And when we look at hardware cost versus licensing cost, the licensing cost far outstrips the hardware cost at this point. And so we find ourselves curtailed by the fact that we aren't going to pay for the additional licenses. And so we're running smaller simulations or fewer of them. Then also multi-physics integration, particularly when we look at the engine modeling, we'd like to get to a position where we have all the internal chemistry of the engine. We also then get that in with maybe the underhood flow, and so start looking at the cooling, and then tie that in with the structural element to look at the loading coming from the combustion and feed that back through our structures and so on. And there are other areas as well where multi-physics integration is an issue. Thinking about hardware, so we have this ever-increasing complexity of the hardware, and internally we're not doing a lot of coding for the parallel applications. We're trying to partner with other sources to do that, but the hardware, we have to start coding very hardware specific, looking at the divergent competing technologies. We're looking at GPUs versus CPUs or mixed systems, and particularly for our internal codes where we need to get some level of parallelization, which architecture do we choose? And so that's an issue. We're trying out several of them, but it'd be nice if we kind of converge on a common architecture. So then finally, where we want to move to is this virtual realism, particularly if we look at the design by analysis. At some point, our simulations have to be as good as what our tests are. And if we cannot predict everything that occurs in the real world, then our simulation, the ability to design by those simulations is going to be in question. So model accuracy, that's an issue. Model resolution. And model resolution is an interesting one because at some point the resolution is beyond what we need, and the question is what's the level of resolution we need. We have some areas of models where the resolution is probably quite low and needs to be increased. We have other areas, hydraulics is one example, where we model all the way down to where there's a poppet valve in the middle of some component and it's running at maybe a couple of kilohertz frequency. Well, it's not necessary when we look at the machine performance. So how do we start to get the right resolution? And then uncertainty quantifications and results as probability distribution functions. You know, a lot of times when we're doing this design, we'll look at say, well, our material strength is this number, and our loading is this other number. Well, unfortunately, the material strength has a distribution to it, and our loading has a distribution to it. And the question is, well, what about, we may think that we're okay here, but in reality, we just under-designed our machine. Well, then we could look at it and say, well, you know, we just want to make sure that our minimum material strength is much higher than our maximum load. And at this point now, we've over-designed, and all of a sudden a cost issue comes into play, and our competition is starting to eat us on that one. And ultimately where we need to get to is that we have some healthy relationship between what's our load versus our material strength. And again, this now drives huge numbers of simulations when we start looking at outputting probability distributions rather than single points. So just a few more things, and throughput is another one, not to spend a lot of time on this, but when we look at speed up, we may look at a code and we want to speed it up by an order of magnitude. Well, that's only one element of this whole throughput. Throughput says from the point that I try to gather my data until I get actionable results, that's what I need to speed up. And so it's not good enough to just say I perform my simulation order of magnitude faster. It's that I need to be able to get actionable results an order of magnitude faster. So that's a key. Another one, software usability. And just to go through this real quick, we think about graphical user interfaces and how can I get the analyst to build this model faster. Just looking at finite element, I'm not going to read through this whole thing, but just thinking about where it came from, where we kind of started off, and just the fact that we got a result, we were pretty amazed by that, to where you needed experts to build this mesh, to where then we got automatic meshers. And then here's a picture which I pulled off, I think this was some software where they actually had finite element, and this happens in a number of different softwares, but you have finite element, very complex modeling that's embedded in a piece of software, and a designer who knows nothing about finite element is able to make design decisions because all the complexity is taken into account behind the scene for him. And this, when we look at our design, the ability to embed virtual product development into a design process, this is key. We are not going to have experts at all levels. So how do we take this technology and put it in a form that they can use it? Okay, and then the final one, and this I think is a big one. If we look at cultural change, and this is probably across many different companies besides Caterpillar, so comments when we think about our product designers. So the old way is going to get the product out the back door. There is huge risk in saying, well, we're going to do something different. The old way worked. There's risk in going to the new way. We're just going to stick with the old way. And this fear of change, also, this is another one we really struggle with, is that we go out to the test, and they get real data, and they see real hardware. They can feel the iron, and to them, that's real. And we come up with a simulation. And maybe it's our wording. Maybe virtual product development isn't a good word, but they view it as being unreal. It's not real. It's kind of fake. It's artificial. So trying to help these designers understand that these results from simulation are as real as the results you get from testing. That's something that needs to be overcome. Also, we can't simulate everything, so we still need to build a prototype. We may have run these tests and maybe we answer 10 different questions. If I can simulate 9 of those, we still build the prototype. So that's an issue. If we cannot simulate everything that we use a test for, we're not going to overcome the need to build that test. So just a final comment. So I think about virtual product development, putting into the design process. We need to focus on accuracy, building confidence. That's a key issue. And then proving the value. Another issue as well, and then integrating with the design process. And this last one I think is very significant. We can have some simulations. We give it to an analyst. We have 1 or 2 kind of maverick analysts. They'll pick that up and they'll use it. But until it's actually integrated into the process and all of the designers are able to take advantage of this, it's not going to actually be embedded into the whole process. And again, the culture, I think, is the biggest issue that we have to overcome. So with that, I don't know if there's time for questions or not.
Questions.
Okay, very well. Thank you.